Yeah, speaking of Chapter 18, we'll have the Chapter 18 test coming up Thursday.
I need to ask some questions.
Yeah.
I had everything written down. I left it home.
Okay. We could go through those tomorrow if you want.
Okay.
Just bring it.
It's a lot of like homework and stuff. I don't know. I can go through the videos and like when I'm going through them with you, it makes sense. But like when I try to do them on my own, I'm completely lost. I don't.
Okay. Yeah, we're going to take a look at those.
Okay. But yeah, we left off on the second one.
Okay. Did we come up with the equation delta G is equal to delta H minus T delta S?
No.
No.
We left off on delta S universal is equal to delta S system plus delta S surroundings.
Okay. The delta S for this would be universe. The delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So delta S of the system is whatever reaction or process you're studying. The surroundings will be the rest of the universe. And then if we know that this is greater than 0, what that means is that this is spontaneous. If it's equal to 0, that means it's at equilibrium. And if it's less than 0, that means it's non-spontaneous. Spontaneous just means it occurs naturally. You don't have to force it to go. And so delta S of the system, we can figure out, because we have appendix D. We can look up, entropries of the final state, entropries of the initial state, and just take final minus initial. But the rest of the universe, we aren't going to be able to do that. But it turns out that delta S is related to heat. So, for example, the more heat that's absorbed, the more waves that can be absorbed, the higher the entropy. And so we'll have delta S of the system, and then what we're going to do with the surroundings is we're going to just say plus Q of the surroundings over T. It's related to the amount of heat at a given temperature.
It's related to heat at a given temperature?
Yeah, right. I'm not going to get into where that comes from, but just to say that the amount of heat exchanged is a reflection of how many ways. So, for example, if you were to heat up some water, water can absorb a lot of heat because there are a lot of ways to absorb that heat: translational motion, vibrational motion, and rotational motion. Compared to heating up a copper plate, if you heat up a copper plate, then you only have vibrational motion. So only one way. And so water is going to have higher entropy. A copper plate at a given temperature. Then we can use the first law of thermodynamics. The first law of thermodynamics just says that if the surroundings loses or gains heat, then the system must have gained or lost. And so Q of the surroundings is equal to minus Q of the system. That's the first law of thermodynamics. Now, heat is not normally a state function. State functions are always the same. So, for example, the time it takes to maybe get to school, is it always the same, or does it vary depending on how you get here? It varies depending on how you get here. So we don't call that a state function. If it varies, then it's not a state function. However, the same thing with the amount of heat. The amount of heat depends on how it gets there. So, for example, if you have a battery, a AA battery, the AA battery can be used to power a fan motor, or it can be used to do other things. And depending on what you use that AA battery, the amount of heat that we're going to get from that battery varies depending on how much work you actually do using that battery. But we can make it a state function. The way we can make like something a state function is always do it the same way each time. If we always do it the same exact way each time, then you should get the same exact amount of heat. So if we only use the battery for one thing, and that one thing is the same every single time we do it, then we can make it a state function. Or the time it takes to get to school. I mean, if you make it the exact same path each time, although, you know, other things can come in there, then you should get to school in the exact same amount of time. And so what we do is we make restrictions to this. And so these are the restrictions we make. We know that delta U, change in internal energy, is equal to Q plus W. And Q is going to equal delta U minus W here. And so what we do here is we restrict this, we restrict this to constant pressure and P delta V work only. So if we only do the same type of work and we do it at the same pressure, then we should always get the same amount of work. If we always get the same amount of work, then we're always going to get the same amount of heat, because delta U is a state function. This is a state function. Work and heat are not state functions. But we're going to restrict the work so we always do the same type of work. If we restrict the work so we always do the same type of work, then what we're going to do is we're going to generate the same amount of heat each time. If we generate the same amount of heat each time, then that's a state function. And so we'll define this as a new state function, delta H, is the change in enthalpy, which is going to equal delta U. Now we're doing minus P delta V work, so that's a minus P delta V. So this is just equal to delta U plus P delta V. And so delta U is a state function. The total energy of a battery is always the same. Let's say P is a state function, pressure, and delta V is always a state function. If there's a volume change, it doesn't matter how you do that volume change. It's always going to be the same if you have the same final and the same initial. It doesn't matter what the path is. So what we do is we make Q into a state function by restricting the work. And that requires constant pressure. So that's delta H here. So we're going to do that here. Normally heat is not a state function, but if we make some restrictions, we can make it a state function so that this is delta S of the system plus a minus, well, actually, the minus delta H of the system over T. Then we're going to multiply both sides by T. So we're going to end up with T delta S of the universe. Actually, excuse me, we'll multiply both sides by negative T. So we're going to have negative T delta S of the universe is equal to delta H of the system minus T delta S of the system. Okay, delta H is a state function now. We're always going to get the same amount of heat. Delta S is a state function and T is a state function. So this is a new state function which we're going to define. Minus T delta S of the universe is is going to be defined as delta G. And delta G is going to be a function of the system here. So delta G of the system is equal to delta H of the system minus T delta S of the system. So I don't need to know what's going on with the surroundings in this case. Everything's in terms of the system. And so this is it. So if delta S of the universe is greater than 0, it's positive, then delta G of the system must be negative, less than 0. And so this is spontaneous. And so we need a negative delta G for something to be spontaneous. I don't know why they had a negative rather than positive, but that's what they end up doing. So this gives us the criteria for driving force for reactions. And the criteria is delta G. In fact, that's what we're going to calculate. So the second law of thermodynamics can be stated in different ways. This is an alternate way of stating the second law of thermodynamics, and that is delta G is equal to delta H minus T delta S. For spontaneous processes, we need a delta G that's negative. And that will be so we have to keep track of certain things that we need to keep track of. And so we need to track the pressure, the concentration, the temperature. The pressure and the concentration, these are standard or non-standard conditions. Temperature is separate though. Temperature we track is at 298 Kelvin or T. And so we'll have a number of equations that we generate from this.
Is that standard or non-standard?
Yes. So if I have the equation like this, what does that mean? Those little superscripts mean that we're under standard conditions. Now, standard conditions we have a standard pressure. The standard pressure is equal to 1 bar or 1 atmosphere. And we have a standard concentration. The standard concentration is 1 molar, but there's no standard temperature. There's no standard temperature. But most of our data is at 298 Kelvin. And so most of the calculations are going to be at 298 Kelvin. So this is delta G at 298 Kelvin, delta H at 298 Kelvin, and delta S at 298 Kelvin, where T is also at 298 Kelvin. And so what we call this is delta G under standard conditions at 298 Kelvin. So let's take a look at some calculations for this.
So delta G at standard conditions, delta G under standard conditions at 298 Kelvin.
Yes. So the example we're going to look at is a process. That is H2O liquid goes to H2O gas. We want to know what delta G under standard conditions at 298 Kelvin is this. And so one way we could do that, there are multiple ways, but one way we could do that is we could figure out what delta H is, and then delta F. And so we can use the delta H as the formation, which is the first column here, and then the absolute entropy, which is the third column here. And so let's go to H2O liquid and H2O gas. So if I look at H2O liquid, the first column, which is delta H of formation, is minus 285.8 kilojoules. The delta H of formation, minus 285.8 kilojoules per mole. And then we go to H2O gas, minus 241.8 kilojoules per mole. And then we could figure out what delta H of the reaction is, or the process, which would be the sum of the delta H's of formation of products. So I have 1 mole of H2O gas times this, so the moles cancel out. Minus the sum of the reactants. Well, I only have one reactant here, so it's 1 mole of H2O liquid times that. So what we end up with is this. We end up with plus 44.0 kilojoules. There's my delta H. The delta H of formation. All right, and then what else do I need? I need my delta S. And so let's look at the absolute entropies at 298 Kelvin. This is delta H of formation at 298 Kelvin. So the entropy of H2O liquid is the third column, 69.91 joules per mole Kelvin. And the entropy of H2O gas would be 180.8 joules per mole Kelvin. And so the entropy is, delta S is just the entropy of the products minus the entropy of the reactant. So I'll just write S final minus S initial. And that's going to come out to 118.8 joules per Kelvin. Okay, then we plug it into our delta G naught equation. Our delta G naught equation is delta H, which is going to be 44.0 kilojoules, minus T, which will be 298 Kelvin, times delta S, which is 118.8 joules per Kelvin. So what I'll do is I'll convert this into kilojoules here, or I can convert this into joules. I'll just convert this into kilojoules. And that is 1 kilojoule per 1,000 joules. And so what happens here is the kelvins cancel, the joules cancel, that leaves me with kilojoules. So these two units work out. And so this comes out to 8.5 kilojoules plus. Plus 8.5 kilojoules means it's non-spontaneous.
What do we do when we convert it to 44.0 kilojoules and we subtract the 298 Kelvin from it?
So I'll do this one here. We're just going to convert this into kilojoules, the second term. We'll do 298 times 118.8 divided by 1,000. Okay, plus 44. 8.5976. See, let me make sure I got this one. 188.18, sorry. I mean 118.18. Try that again. So 298 times 118.18 divided by 1,000 plus 44. Oh, did I screw that up? Let me do this one line. 188.8 minus 69.94.
118.89.
118.89.
Yeah.
All right, 118.89. So this should be 118.89 here. So let me recalculate that one more time.
Oh, I see. Okay. I see that.
We just have to make sure the two units are the same.
Yeah, I was just confused because I thought that right there was you converting the kilojoules to joules
No.
for just the delta H. I see now.
Okay. So that I get 8.57078 kilojoules. And so that's positive. So the second law of thermodynamics says that's going to be non-spontaneous. So in other words, under normal conditions, that is room temperature and regular atmospheric pressure, water does not boil.
There's 1,000 joules for every 1 kilojoule.
Yeah.
Oh, that sounds okay.
I could convert this to joules as well.
Yeah.
Okay, so according to the second law of thermodynamics, this is non-spontaneous. So water doesn't boil. This is boiling here with vaporization spontaneously. Room temperature. However, we can also do this at other temperatures. That is, delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. So we can do this at different temperatures. So the problem is
Question. So just for that last equation, sorry, I'm just not getting up to the answer. 8.57. So you said that would be, since delta G is, so since it's greater than 0, so less than 0,
yeah,
it's not spontaneous.
it's non-spontaneous because it has to be less than 0.
Less than 0.
So what this means is that the entropy of the universe is actually going down, not up. We need the entropy of the universe to go up. And so if this were negative 8.5, then the entropy of the universe would be going up since they're opposite sign. The situation that we have, though, is let's say we want to at some other temperature. What's happening in this particular equation is this. We can break this down into plus 44.0 kilojoules minus, came out to, what did that second number come out to?
35.
Yeah, 35.
Yeah, 35.429.
Yeah, minus 35.429 kilojoules. So we have a situation here where the enthalpy is saying no, because enthalpy is not favorable. In nature, what we want to do is we want to minimize the energy. That is, we want the energy to go down. So delta H should be negative. That would be favorable. However, in this case, if we look at the entropy is favorable because we're going from liquid to gas. As we're going to liquid to gas, then that's favorable. But it's not favorable enough. It's not favorable enough to cancel out this energy. So the energy is 44, and then we have this entropy, which is T delta S, which is minus 35. We need to adjust the temperature. If we make the temperature bigger, then we can cancel out this. Do you see that? So if we can make this temperature bigger, then we can go 44 minus 44, and then we cancel that out. And then if we go bigger yet, we can go negative. And so by adjusting the temperature, we should be able to make this go negative. And so right now we're at plus 8.5. So what we need to do is, we need to do this. This is delta T at temperatures other than 298. So T is not equal to 298 Kelvin. So what we want to do is we want to set it so that the T delta S term cancels the delta H term. In other words, we need to transition from positive to negative. So what we're going to do is we're going to set delta G naught at temperature T equal to 0. And that's going to transition from positive to negative, and this is going to equal delta H naught at temperature T minus T delta S naught at temperature T. So what we need to do is we need to go from plus 8.5 to negative. And in order to do that, the transition point said 0. And so 8.57.
Transition point says 0 because when you're below 0, that's when
it goes spontaneous, right? So we need to go from non-spontaneous to spontaneous. So we need to decrease this until we hit 0 and then go negative. And so this is why we're going to set it to 0. We're going to set it to 0 to make it spontaneous. And so what that's going to mean is that the T will solve this equation for T. So T is going to equal delta H naught over delta S naught. So that's the temperature at which, if I increase the temperature to this point, then I'll be able to cancel out the plus 44 kilojoules, which is preventing the reaction from occurring. Problem is I don't have delta H at temperature T. In fact, I only have delta H and delta S value at 298 from 10x D. But what we're going to do is we're going to say this, that the delta H value at temperature T is going to be about equal to the delta H naught value at 298 Kelvin. And the delta S naught value at 298 is going to be approximately equal to delta S naught at 298 Kelvin. And so this will allow us to estimate the temperature at which it will transition to spontaneous. So this is 44.0 kilojoules divided by delta S, which is 118.89 joules per Kelvin. Now this 44 kilojoules, well, we're going to just convert that to joules. So I'll have 44,000 joules divided by 118.89 joules. And then the Kelvin will come up on top. So the joules cancel. So let's see what that comes out to here. So this will be 44,000 divided by 118.89. 370. We already know. Do you know? I already know the temperature at which water boils. What temperature does water boil at? So in order to make this happen spontaneously, one way to do that is to increase the temperature. So if I want to convert water into steam, I'll increase the temperature to 100 degrees C. At 100 degrees C, it should boil. 100 degrees C is equivalent to 373 Kelvin. And so this calculation should have come out to 373 Kelvin because that's at the temperature at which it starts to boil. It came out to 370 Kelvin, but really we needed the delta H at 373 Kelvin and the delta S at 373 Kelvin, which we didn't have. So we had to use these at 298. So it's off a little bit. So this is example calculation, delta G under standard conditions, but at a temperature other than 298 Kelvin. What if when atmospheric pressure is equal to vapor pressure? So when the vapor pressure is equal to 1 atmosphere, that's called the normal boiling point. Although this is 1 bar, sorry. So the boiling point of water is slightly different. At 1 bar. And so the error is not as far off as you might expect. What if we're under non-standard conditions? That is, what if we're like at a pressure not of 1 bar or 1 atmosphere? 1 bar and 1 atmosphere are pretty close to the same. What if we're at a pressure that's a bit higher or a bit lower? So this is non-standard conditions. The equation for non-standard conditions is just a correction to standard conditions. So if we want delta G under non-standard conditions, we can't use that little superscript here. And so we could do delta G under non-standard conditions at 298 Kelvin. This is going to equal delta G naught under standard conditions at 298 Kelvin, plus a correction. And the correction is RT ln of Q. And so we take our standard conditions and then it's corrected. And Q is going to be the reaction quotient. This will be at 298 Kelvin. So what we can do is do this non-standard conditions at 298 or at temperature T. So delta G at temperature T is equal to delta G naught at temperature T plus RT ln of Q. And so these are the two equations. So let's say we're looking at water boiling at 1/3 of an atmosphere. So H2O liquid goes to H2O gas. Q is equal to the partial pressure of H2O gas divided by 1. Liquids have an activity of 1. And so this is just equal to the partial pressure of H2O gas. Boiling occurs when the partial pressure is equal to atmospheric pressure. So let's say in our example here, we want to boil the water on top of Everest. So at high altitude, the summit of Everest, Mount Everest, has a pressure of about 1/3 of an atmosphere.
Is that supposed to be Q equals the partial pressure of H2O liquid?
Gas.
Of gas.
Yeah. Partial pressure of H2O gas.
Partial pressure of H2O gas over 1 is equal to the partial pressure of H2O gas.
Right. It's the products of the reactants.
Oh, I see. Okay.
So the products would be H2O gas and reactant H2O liquid. This is the first part. This is a thermodynamic, so if it's a gas, we use partial pressure. If it's an aqueous solution, we use polarity. So at the summit of Mount Everest, we're under non-standard conditions, so this pressure is not equal to 1/3 of the atmosphere. At what temperature will water boil? What T will water boil? So what we're going to do is we're going to try to figure out this. So the first thing I might try is this. What we just did, the calculation. That is, right now, under standard conditions, delta G naught is equal to plus 8.57 kilojoules. And so what I want to do is I just want to bring that to 0. This was equal to delta H naught minus T delta F. So if I bring delta G naught equal to 0, then it should boil. When I get delta H naught minus T delta S. And then T delta S naught is equal to delta H naught. And T is equal to delta H naught divided by delta S naught. And so we got 370 Kelvin. But the problem with this is under standard conditions. What we're doing is we're doing non-standard conditions. So this is the wrong equation to use. For non-standard conditions, we need to use a different equation. So if we're doing non-standard, then delta G under non-standard conditions is equal to delta G naught under standard conditions plus RT ln Q. So what we're going to do is we're going to solve this for T. So the first thing is I'm going to make delta G equal to 0, because what I want to do is I want to transition from this positive from 0 to negative. This is going to equal delta G naught plus RT ln Q. And delta G naught is equal to RT ln Q. And T is equal to delta G naught over R ln Q. We get to the temperature. Okay. So we'll do this. But we have a problem here. The problem is this is delta G at what temperature? 290 Kelvin or T?
Isn't that T?
Yeah, this is going to be T because we don't know what the temperature is. So this is delta G at temperature T, which is equal to delta G naught at temperature T. And then the Q is going to be at temperature T. The problem arises here. In order to calculate the temperature, we need to know what delta G naught is at that temperature, T. Because delta G naught changes significantly with temperature. We saw that we were able to make water boil spontaneously by increasing its temperature. And so we can actually switch it from a positive delta G to a negative delta G, going through zero. In order to solve this for T, we need to know what delta G naught at that temperature is. We don't have that. And so we can't solve this. In other words, we cannot do this. This is not equal to delta G naught at 298 Kelvin over R ln of Q. The reason is because delta G naught is a function of temperature, and delta G naught changes significantly with temperature, changes significantly with temperature. So we're stuck here. We can't use this particular equation for this. Well, how did we calculate delta G at different temperatures under standard conditions? So instead of doing this, what we're going to do is this. We calculated delta G under standard conditions at, what does that say under delta G of T? Changes significantly with temperature. We're going to substitute that in here. What we're going to substitute in is delta G naught at temperature T is approximately equal to delta H, well, I'll do that here. Delta H naught at temperature T, or delta S naught at temperature T. Actually, it's equal to. And so what we're doing is, instead of having this as delta G naught at temperature T, we've got to figure out what that is. And so the way we're going to figure it is by using this equation here, plus RT ln of Q. So what we're going to do is we're going to set this equal to 0 here. And this is going to be about equal to delta H naught at 298 Kelvin plus T delta S naught at 298 Kelvin. And so that is delta H at temperature T is approximately equal to delta H at temperature 298 Kelvin. And delta S naught at temperature T is approximately equal to delta S naught at 298 Kelvin. However, delta G naught at temperature T is not equal to delta G naught at 298 Kelvin. So we're going to use these. Plus RT ln of Q is equal to 0. Then we're going to rearrange this equation here. I'm going to subtract the RT element of Q from both sides. Actually, no. I'll subtract the delta H from both sides. Let's do that. So I'm going to get T delta S naught at 298 Kelvin plus RT ln of Q is equal to minus delta H naught at 298 Kelvin. If we factor out the T here, we're going to get T delta S naught at 298 Kelvin plus R ln of Q is equal to minus delta H, 298 Kelvin. Then we're going to divide both sides by this term here. So we're going to T is equal to minus delta H naught at 298 Kelvin divided by delta S naught, 298 Kelvin, plus R ln of Q. Okay, so let's plug the numbers in here. Delta H is minus 44. I'm going to go joules, 44,000 joules. Delta S is 118.89 joules per Kelvin. R is 8.3145 joules per Kelvin. Times ln of Q, ln of 1/3. So let's see what the temperature comes out to. I'll just start off, we're going to start off with natural log 1/3. 1 divided by 3. Natural log times 8.3145. Plus 118.89. Invert that. Times minus 44,000. Of 400.89. 400.89 Kelvin, that can't be correct. To get a vapor pressure of 1 atmosphere requires a temperature of 373 Kelvin. And so I made a mistake here. Let's try to find my mistake. Or I made a mistake in my calculation. Oh, I see my mistake. My mistake is here in the sign. Delta G is equal to delta H minus T delta S. I put plus. Minus T delta S. We have to, the signs always get mixed up here. For example, here, this is the correct sign. This is plus RT ln Q. One quick way to check this is as Q gets bigger, Q is products of reactant. As the Q gets bigger, we have more and more products, which lowers the driving force, which should mean that delta G becomes more positive. So as Q gets bigger, delta G becomes more positive. This is different here. So this is delta H minus T delta S. So if I subtracted that, this should be minus T delta S here. This is minus delta S. And minus delta S. And so let me try that again. So I get, let's do the natural log 1/3. So 1 divided by 3, the natural log of that, times 8.3145. Equals minus 118.89. Invert that. Times minus 44,000. So it comes up to 343.68. Which is equal to 70.68 degrees C, or about 71 degrees C. So, yeah, great. Okay. So let's say we're at the top of Mount Everest. If you're at the top of Mount Everest, the pressure is about 1/3 of an atmosphere, or 1/3 of a bar. If you boil water here, you don't have to get it as hot because we just need to create 1/3 of a bar of vapor pressure, which doesn't take that much temperature. It only takes 71 degrees C. So in other words, water boils at 71 degrees C at the summit of Everest. And that has implications on cooking. That is, what do you use boiling water for? You use boiling water to cook different things. So, for example, cooking pasta. You use boiling water to cook pasta. Cooking pasta on Mount Everest is going to take a lot longer because the temperature is a lot cooler than cooking it at sea level. Cooking pasta at sea level, the temperature is at 100 degrees C rather than 71 degrees C. And they say for cooking, every 10 degrees C doubles the rate of reaction. So if you went from 71 degrees C to 81 degrees C, then that's going to basically cook things twice as fast, which means that the time is going to be cut in half. And so from 71 to 81, things cook twice as fast, and then 81 to 91, twice as fast, and then 91 to 100, twice as fast again. And so cooking things at 71 degrees C is going to be awfully slow. Awfully slow. Can we boil water at room temperature? Can you imagine cooking pasta by soaking it in room temperature water? It's how long is it going to take to boil the pasta? In other words, how long is it going to take to cook the pasta? And so let's take a look at the video.
Degrees Celsius is around 160 degrees Fahrenheit?
Yeah.
So the normal boiling point of water is being 100 degrees Celsius, but that is because we are at 1 atmosphere pressure. This water is currently 21 degrees Celsius. We're going to evacuate the jar and make the water boil. As the pressure surrounding the water decreases, it allows the water molecules to escape. We can see that the water is boiling, and we might expect it to be 100 degrees Celsius, but let's check its temperature again. As you can see, it's very close to its initial temperature. The water boiled, the temperature didn't change.
So we'll do another calculation here. And this calculation will be about what pressure will water boil at room temperature. Room temperature being 298 Kelvin. They're below. They're at 21. We'll do it at 25 degrees C. The first thing is, this is not standard pressure. You know, standard pressure is 1 atmosphere or 1 bar. And we already know what temperature water boils at standard pressure. Water boils at about 100 degrees C. You know, at 1 atmosphere, it is at 100 degrees C. At 1 bar, it's slightly less. And so at what pressure will water boil at room temperature? Well, we need non-standard conditions. We need non-standard conditions, and we need non-standard delta G, non-standard delta H, minus T, delta S, non-standard. We don't have delta H and delta S under non-standard conditions. We have delta H and delta S at 298 under standard conditions. Now, if we change the temperature but retain standard conditions, then we can use it. And so we don't have that. So what we'll have to do is we'll have to do this. We'll take our delta G naught and then direct it, or T on Q. So we're going to make it boil. Now, there's one thing I didn't do earlier, and that's this. When delta G is equal to 0, we're at equilibrium. If we're at equilibrium, then we know that Q must equal K. So delta G equals 0 means at equilibrium. Therefore, Q must equal K. The condition we're given is equal to equilibrium condition. And so what we're going to do here is we're going to set delta G equal to 0, and then this is going to equal delta G naught plus RT ln of Q. But if we're at equilibrium, then Q is equal to K, so we can substitute K instead of Q here. Now, if we're looking at H2O liquid goes to H2O gas, then Q or K it's the same thing. This is going to be the thermodynamic, so this is going to equal the partial pressure of H2O gas over 1. It's unit activity. So we're going to solve this. Delta G is equal to 0 because we want to make this spontaneously boil under non-standard conditions by changing the pressure using the RT ln of pressure of H2O gas. Okay, now we need to know what temperature we're dealing with. And so I didn't want to use their temperature because I don't have data at 21 degrees C or 20 degrees C. But I do have data at this temperature. So if we do delta G at 298 Kelvin, set that equal to 0, this is going to equal delta G naught at 298 Kelvin plus RT ln K. So delta G naught at 298 Kelvin is no problem. You know, there are multiple ways of calculating delta G naught at 298 Kelvin.
So we're no longer doing the delta G plus RT ln partial pressure of H2O?
We are. I'm sorry, this is going to be partial pressure.
Oh, okay.
H2O. Delta G naught at 298, there are two common ways that this is solved for. One way of doing this is delta G naught at 298 Kelvin is equal to delta H naught at 298 Kelvin plus T or minus T delta S naught at 298 Kelvin. We'll just plug in a temperature of 298 Kelvin for T. Or this one is kind of tedious because we have to do these two calculations. There's an easier way of doing that. If we want delta G naught at 298 Kelvin, then this is just equal to the sum of the delta G's of formation at 298 Kelvin of the products minus the sum of the delta G's of formation of the reactants times the number of moles of each, which is given by mu. So we had already calculated this one earlier. This one came out to plus 8.5 kilojoules, 8.57 kilojoules. So let's compare that with this alternate method. This alternate method should work. So we use the first column and the third column. This middle column is the delta G's of formation. This is going to be the easiest way to calculate delta G of formation at 298, or delta G at 298 Kelvin. So in this case, we have, this is the reaction we're looking at. 1 mole of H2O liquid goes to 1 mole of H2O gas. So we need the delta G of formation of H2O gas. The delta G of formation of H2O gas is up there, minus 228.6. So we have 1 mole times minus 228.6 kilojoules per mole. The moles cancel. Okay, minus the sum of the delta G's of formation of the reactants. So the reactants H2O liquid. H2O liquid is minus 237.1. So minus 1 mole times a minus 237.1 kilojoules per mole. So what does that come out to? So let's see. 228.6, actually 237.1. 237.1 237.1 minus 228.6 is 8.50 kilojoules. So earlier we got 8.57, here we got 8.5. So, you know, they're close, but they should be exactly the same. But because, you know, how the numbers were determined, they're different, you know, than experimental error. So these are two ways. The second way is a lot less work, but the second way you can only do at 298 Kelvin because we only have delta G of formation values at 298 Kelvin. And so this only works at 298 Kelvin, whereas this first way we can do at different temperatures. Including 298 Kelvin. If we make the assumption that delta H and delta S don't change much with temperature. So we're going to rearrange this equation here. And that is delta G naught at 298 Kelvin is equal to minus RT ln of P H2O. For the P of H2O, I'm also going to just call that K. Well, the reason I'm going to call it K is because of this. I'm going to get minus delta G naught over RT at 298 Kelvin is equal to ln of K at 298 Kelvin. And then solving for K at 298 Kelvin is equal to e to the minus delta G naught at 298 Kelvin over RT. Okay, this is equal to the partial pressure of H2O liquid. And so delta G naught at 298 was minus 8,570 joules over 8.3145 joules per Kelvin times 298 Kelvin. And we're going to raise E to that. Let's see what that comes out. So 8.57 with the negative divided by 8.3145. Divided by 298. Take e to that. Oops. Error. 8,570 divided by 8.3145 divided by 298. All right, K is equal to this, and therefore the partial pressure of H2O, K is dimensionless, is going to be equal to 0.03146 bar. This is going to be 0.031 bar. So we have to drop the pressure to from 1 bar to 0.03 bar. And so we'll need a pretty powerful vacuum to do that. And once I suck out the air, the vapor pressure water is going to equal that. In fact, I can use this equation here for the vapor pressure of water at 298 Kelvin. The vapor pressure of water is going to increase exponentially like that. So So at 1 atmosphere, we have 100 degrees C or 373 Kelvin. If I go to 1/3 of an atmosphere, then it came out to about 340 Kelvin. If I go to 0.031 atmospheres, then it's going to come out to 298 Kelvin.
So how do we know that this is in bar?
Because this table tells you at the beginning. Thermodynamic properties of substances at 298.15 Kelvin. Substances are about 1 bar. So that's why.
I thought that the R constant was that in atmosphere?
No, this this is the other R. We have 2 R constants.
Right. The other one, I thought the other one was the bar constant. The 113 something.
I'm using the wrong R. You're right.
Oh, okay. I thought.
Yeah, I should have corrected that. I'm just going to be introducing slight errors to this.
Okay. Yeah.
That should be more consistent.
But that bar, is that in kilojoules or joules? Is that one that has? Yeah. How many joules per mole? Kelvin? Yeah.
This one's in joules. Oh, Kelvin.
I can't remember the other one. It was like 101, 305. I can't remember the actual.
Well, this is in 0.08206 liters atmosphere per mole Kelvin. And then we can multiply this one here by bar. Actually, this is the easiest way to do this. So the easiest way to do this here is we've got 8.3145 joules per mole Kelvin divided by 0.08206 liters times atmosphere per mole Kelvin. So the mole Kelvin cancels. And this gives us 101.32 joules per liter atmosphere.
Also, it is joules.
But the other thing is, this is per liter atmosphere, not per liter bar. Or 101. Actually, let me calculate that again. Does that come out to? So we'll take 8.3145 divided by 0.08206. 101.32 joules per liter atmosphere. Now, in 1 atmosphere, there are 1.01325 bar. This is 101.32. Actually, I'm only allowed 5 sig-figs, 4 sig-figs anyway. So I'll do this divided by 1.01325. Which gives me 99.997 joules per liter bar. I'm only allowed 4 sig-figs, so I need to round this. And this is going to round to 100.0 joules per liter bar. problem is, people use both atmospheres and bar, and the data sometimes you don't know. Is it in bar or is it in atmosphere? And so that's a problem. But fortunately, it doesn't lead to a huge error, just about a 1% error, 2% error, a few percent error. It's not huge. So even if I use the wrong one, so this brings up another equation that's quite handy, and that is delta G naught is related to K. And delta G naught is equal to minus RT ln K. And so this is delta G naught at temperature T, which is equal to K at temperature T. Or we could do K at temperature T is equal to E to the minus delta G naught at temperature T over RT. If we don't have delta G naught at that temperature T, then we can calculate what it would be by using this. And so this is going to be minus delta H naught at temperature T minus T delta S naught at temperature T over RT. Which is going to equal about equal to E to the minus delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. So this will be under standard conditions here over RT. Figure it out that way. Likewise, the same thing happens here. Well, actually, we're calculating delta G naught at that temperature. So we can figure out that KT at different temperatures here. We can also figure out delta G at different temperatures. Now, if we go under non-standard conditions, we'll have delta G is equal to delta G naught plus RT ln of Q. So if we make this under non-standard conditions, then we want to figure out what K is. Delta G is equal to 0, which is equal to delta G naught plus RT ln of K.
Wait, I'm confused. What are we doing here?
Well,
I want to find KT. I got that part up there with the E raised to all of that. So what are we doing down here?
okay. What we're doing here is coming up with one more relationship.
Okay.
And that is, let's say I'm solving for T in this case. If I'm solving for T here, and what I'm going to end up with is delta H naught at temperature T minus T delta S naught at temperature T is plus RT ln of K. And we set this equal to 0 again. And then I'm going to get the T terms on one side and the H term on the other side. And so I'm going to go RT ln of K minus T delta S naught is equal to minus delta H naught at temperature T. T, factor out the T, R ln of K minus delta S naught at temperature T is equal to delta H minus delta H naught at temperature T. This is one more equation. And so T is equal to minus delta H naught over R ln of K minus minus delta S naught. Or some variant of that equation. So that's the equation here versus here. This is delta G naught at temperature T, delta G at temperature T. So if I set this one equal to 0, then this is equal to delta G naught plus RT ln of K, which gives me this equation here. Delta G naught is equal to minus RT ln of KT, which goes back up here, which gives me this equation. That is, T is equal to, solve this equation for T, I get negative delta G naught over R ln of K. And so compare these two equations here. If I compare this equation versus this equation, why are they different? Well, maybe this one I just need delta H and delta S, but this one I just need delta G at temperature T. This one turns out to be impossible to solve. Why is this one impossible? That is, this one just comes from this, goes down to this. The reason this one's impossible to solve is because in order to get delta G naught at temperature T, we need to know what that temperature is. If we don't know what the temperature is, then it's impossible to solve it. Are we out of time? Okay. Versus this one, we don't need to know what delta, although we need the temperatures here, we can estimate it by saying that the delta H and the delta S don't change much with temperature and just use the values at 298. So the best way to do this is through practice, which we'll do.